Uh, okay, so welcome. Good evening, everyone. Today I am going to discuss about the week 8, the assignment 8 of the previous year assignment. So, as you all know, that it's E602 tutorial class of basic electronics. The normal basic electronics course is taken by Professor Mahesh Patil, and I am Subhajit. I am the PMRF from IIT Bombay. So this course entire duration is about 12 weeks, and it is scheduled in every Tuesday from 6 p.m. to 8 p.m. So today we'll generally cover some topics about the week 8 assignment. So let's begin. Okay. Okay. Uh, so basically we will today we will cover some topic regarding the basic op-amp circuits. The op-amp basic circuits have already been covered, so it's some advanced version of the op-amp circuits. So we will cover the op-amp circuits, and then we will talk about some active filter. Active filter means we have previously done the analysis about the passive filters. So these passive filters means. Okay, so passive filters means basically the filters that is made of the passive elements. Passive elements refers to resistor, inductor, capacitor, RLC circuits. All are there. So we have already seen some circuits like RC circuits, some low pass filter, and also some high pass filter. So if we are giving input and we are collecting output from any terminal, from the other terminal, then we can see that how it behaves, and so as a result it can act as a filter. So these all circuits are known as basically passive filters because the elements are basically passive. There is no active element in that. But here we will discuss some active filter where the active element is op amp. So mainly op amp filter we will study some op amp filter. Basically the use of the active filter is that to boost the signal or to amplify the signal, and then it can be easily used as a filter. Okay, so this we will discuss, and then we will discuss about the some precision rectifier, how it can be built, and how the operation of the basic precision rectifier circuit of using op amp. So this op-amp precision rectifier, and at last we will study some of the basic concepts about Bode-Plot. So we'll discuss all of the things. So the Bode-Plot, the basics, how we can form the magnitude plot and also the phase plot. All of these things we will cover one by one. Okay. Yeah. So basically we will cover all these things using some problem statements, and these are all the previous year assignment. So these are previous year assignment questions, so we will discuss one by one each of the question, and we analyze each of these. Okay. Yeah. So moving forward, this is the first question. Which of the following plots correctly describes the VO versus VI relationship for the circuit shown in figure? So, as I have already discussed, that VO versus VI relationship often it is known as transfer characteristics. Transfer characteristics. Transfer characteristics. Okay. So basically, we have certain categories. Suppose we have some input with respect to T, Vi with respect to T, and then we get some output with respect to T. It can be time domain or it can be frequency domain as well. These are the normal characteristics, but when we plot the output characteristics with respect to the input characteristics, then it is known as the transfer characteristics. So basically in this question it is asked about the transfer characteristics for the circuit given in figure. Okay. Yeah, so this figure has a basic op amp and one Zener diode. So as I have already discussed, so this Zener diode, So basic symbol of this Zener diode is like this. So this is a Zener diode, this is the anode and this is the cathode. So this terminal is referred as P positive and this is negative. So the basic characteristics of the Zener diode is it can act as a normal diode, and also at the reverse bias region it can act like this. Is the normal characteristics of a basic Zener diode. Okay, so this is the current versus voltage characteristics of Zener diode. So basically, uh, what happens is when this input voltage, that is the uh, V anode to cathode, it is greater than zero point 0.7 volt. So we have also idealized this model. This is the idealized model. Let go to the idealized model. So in the idealized model we have already discussed that after certain voltage, which is known as threshold or cut-in voltage, uh, yeah, so this is basically this threshold voltage or cut-in voltage or knee voltage. So after this voltage there is basically infinite amount of current flowing through the circuit, flowing through the diode, but the voltage has a some fixed value. So this is the model. And similarly in the reverse bias also, so this thing, so this is known as the Zener voltage, or we can say as a knee voltage also. So this is basically negative. Suppose it can be minus 6 volt or it can be minus 7 volt, like that. For and this cut threshold voltage or cut-in voltage around zero point 0.7 volt, like that. So in between this it can be act as an open circuit. Open circuit means, that means there is no flow of current through this. You can see the current axis, the current is zero, and after that it can act as a short circuit, it can act as a short circuit. So this is very idealized model. Also you have some other model where you can say like after this cut-in voltage there will be some certain there is a on resistance of the diode, and that is inverse of the slope from the inverse of, because it is the I versus V, right? Slope is I versus V, but resistance is V by I, so it is 1 by slope. So using that 1 by slope we can determine the add-on resistance, and we can include that in the picture. And also we can include the battery plus resistance model that I have already discussed in the earlier classes. Okay, so now today we will discuss about this. So similar is the thing for the negative bias too. Okay, so now today we will discuss about this ideal Zener diode model. So this is a basically Zener diode. So this terminal is positive terminal P and this is N. So this is P terminal and this is N terminal. And now how we can discuss? So this is a basic op-amp model, right? Okay, so at first we will analyze this thing. So mm, for analyzing any op-amp circuit, I have already discussed that we have to look into two things. First of all, it is not mentioned that it is non-ideal op-amp. If in the question it is mentioned like non-ideal op-amp, then we should consider that only. But if it is not mentioned, then we'll consider it as ideal op-amp. So it is an ideal op-amp, and also it has some negative feedback. Why negative feedback? Because there is some path, the feedback path between the output to the inverting terminal of the op amp. So it is a negative feedback. So as a result we can use the concept of virtual short. So as I have already discussed that for the op amp the output is nothing but the open loop gain. AOL is open loop gain into the voltage difference across these op amp terminals. Okay, so it can be written like AOL into V plus minus V minus. If this is V plus, this is the V plus, and this is the V minus terminal voltage. So we can write like this, or in the other way we can say like this VID. This VID is basically VO versus AOL. Now the open loop gain of op amp is, for the ideal op amp, is infinite. So we can say this VID is equal to 0. Or in other way we can say V plus minus V minus is 0. or we can say that V plus is equal to V minus. So whatever the voltage we are applying in either of this terminal, the other terminal also sees the same voltage. So this is the concept of virtual short, of which a special case is virtual ground. Virtual ground is a special case. That means if we put any terminal ground among these two terminal, then the other terminal automatically will ground. But the conditions are, at first it should be ideal op amp and it should have negative feedback. Okay, yeah. So we are seeing that thing only, and also it's so it is the case of an inverting op amp. Why inverting op amp? Because we are applying the input voltage to the inverting terminal, Vi, in the inverting terminal, not in the non-inverting terminal. So it is known as the inverting op amp. Okay, so it will behave basically as an inverting op amp. Okay, so what is happening? So I am discussing with discussing in case by case. So for case 1, so this is the case 1. So case 1, so case 1, if Vi is equal to 0 volt, so when Vi is equal to 0 volt, what is happening? So it's Vi is 0 volt, and this is the also so it's the 0 volt because it is ground, actually connected to ground. So according to the virtual short concept or virtual ground concept, this V, as V plus is equal to ground, so V minus will be also equal to V plus. That means it is a virtually ground. So this terminal is at ground potential and Vi is also ground 0. That means no current will flow through this, right? If no current will flow, so Vi is equal to 0, no current will flow through this. So what will as we know, in the ideal op amp, the ideal op amp does not draw any amount of current inside this. So basically whatever the current flowing through this terminal will be flowed through the feedback path, right? So here also there is no current is flowing through the input terminal, and as a result, input terminal means in the input resistance side. Okay, so no current will be flow through this path. So as a result, the output should also be 0 volt. So while Vi is equal to 0, it refers to Vo is also equal to 0 volt. Now what happens if we increase the Vi? So case 2, so Vi is equal to small positive. So when Vi is small positive, that means Vi is just greater than 0 volt, then what happens? Certain amount of current will flow. So I will draw the circuit. What happens? Mm, just a second. Okay. So I will draw the circuit again. So for this small positive, so small positive, that means whenever this in this region, in this terminal, so in this terminal, this is the diode is in open as act as an open circuit, because the diode doesn't conduct before it comes at 0.7 volt, right? The cut-in voltage. So basically the circuit will be like this. So it is inverting terminal, this is RL, this is PO, this is 2R, this is R, and this is Vi, and this terminal is open circuit, right? Okay, so this is basically the inverting configuration. So the output Vo versus Vi will be nothing but minus 2R by R, right? Whatever is in the feedback path divided by input path, right? So Vo will be minus 2 Vi. So if we plot, so if we plot the output versus input, so here I am plotting the output versus input. So it is Vi, it is Vo. So in the first case, when Vi is equal to 0 volt, Vo is equal to 0 volt. So this is the case 1. Okay, So this point is case 1. So the in the second, VO is minus 2 of VI. Now VI is small positive, so it will be minus 2 times VI will be the thing, right? So it will be increased like that. This is the case 2. Okay. Now we will discuss about the case 3. So case 3, whenever this VI is greater than threshold voltage or cut-in voltage, then the diode turns on. Now here the diode is off, diode was off, right? But here now the diode turns on. So whenever the diode turns on, then the circuit becomes, so it is 2R, it is R, it is VI. So here the circuit will behave like this. So this is zero point 0.7 volt, right? It is minus negative terminal and it is positive terminal, okay? And this is output VO. So what happens is, so this is ground, so this terminal also becomes the ground. It is also becomes the virtual ground using the virtual ground concept, and this VO terminal sticks to minus 0.7 volt. So after that, if we increase VI more, then also the VO doesn't change, it will be fixed into minus 0.7 volt. So it will be fixed into minus 0.7 volt. So this is the minus 0.7, this is minus 0.7 is in case of silicon. In case of other material like gallium arsenide, this will be changed. So basically so that will be changed in case of other material, but here, so here we can see this is the minus 0.7 volt, something like that. Okay, yeah. Okay, and then the case 4. mm, so case 4, so here this is the case 1, this thing is case 1, this thing is case 2, and this thing is case 3, right? It will give a certain voltage, but infinite amount of current will flow through that. So whatever the, if we increase the VI, then the current also will increase, right? In this, from this terminal the current will also increase, but that extra amount of current can easily pass through this diode, and the output voltage will be fixed. Of course there is a certain limit of this current, because there is some power constraint, that is when we buy a diode, we can see there is a maximum power that is written across the diode. That means maximally that amount of power it can draw. So if the voltage is fixed like 0.7 volt, then 0.7 into the current, that is the maximum current, is equal to P max. So that amount of maximum current can flow through the diode. After that the diode will actually burn. Okay, okay, so this is the basic concepts. And case number 4 is that when Vi is small negative. So when it is small negative, that is uh, just less than 0 volt, so then also the diode acts as an off. Okay, why off? Because this is this region, right? So this is the case 4, this is the case 4. So then also it will act as an open circuit. So the same thing like this, and from here also you can see that VO by VI is nothing but minus 2R by R, right? How minus 2R by R comes, we can do a short analysis, but it is better that we can remember this formula. Okay, that for the inverting amplifier the gain is minus RF by R1, where RF is the feedback path resistance and R1 is the input resistance. Okay, we can do like this: Vi minus 0 by R, because it is ground, so 0 by R equal to 0 minus V0 by 2R, right? So V0 divided by Vi equal to minus 2R by R, which is minus 2. Okay, so similar is the case for here also. So RR cancels out, so it will be minus 2. So in other way you can say VO is equal to minus 2 Vi. So VO is equal to minus 2 Vi. Now Vi is small negative, that means VO will be positive. So similarly this will increase So this has a slope of -2, right? Okay, -2. Okay, so this is the case 4. Okay, this is the case 4. So this is case 4. This is the case 1. This is the case 2. This is the case 3, and this is the case 4. Okay, okay. So now the case 5. So if we increase, if it is greater than the Zener voltage, that is the Vz. So what happens is, so if we increase this thing, so basically what happens, so this terminal is uh, okay. So what happens is, so VO is basically increasing, so it is increasing, VO is increasing, it is increasing, and this terminal is 0 volt. So so now at a certain time it happens that this point is basically this VO, and this point is ground, so it exceeds the Zener voltage. So this negative terminal is much more higher than the positive terminal, so that the Zener breakdown occurs, so it is greater than Vz. So what happened, it greater than Vz, then again the diode, the circuit, I am drawing the circuit again. So this is minus, this is plus, this is ground, there is a resistance, this is Vi, and here also this is 2R, and here we have certain the opposite direction, right here. Yeah, so this is minus, this is plus, this is Vz. Okay, so this is VO. So as it is ground, so the constant Vz voltage, VO will get constant Vz voltage. So Vz is basically the positive voltage, that so VO is constant at Vz voltage irrespective of the input. Means if we decrease the Vi even more, then also the VO become fixed, that is Vz. So it will be fixed over Vz. So I am considering about this case. Okay, this case. So this is case 5. Case 5. Okay, so this is case 5. So it will be constant about Vz. So this is the thing, the VO versus Vi relationship. So according to the options, given options, so option B is correct because it is matches about with our answer. So this is the correct answer. So the transfer characteristic will look like this. Okay, yeah. So remember here the this diode is on, and the Zener diode is on, it acts in the reverse bias. Here the diode is on, and also it can act as an uh, normal diode. The Zener diode acts as a normal diode, and between these two the normal Zener diode is off, so we get a gain of minus, constant gain, that is -2. Okay, yeah, fine. Okay, so I am moving to the next problem. So this is a basic question about the op-amp. So how the in the op-amp circuit, how the output versus input, how it can act. So it's a basic question. Okay, yeah. So the next question: what is the form of the transfer function for the circuit shown in figure? Okay. Now here we should know about what is the transfer function of a circuit. Suppose there is some system. So here we have some system, and we are giving some input, and we are getting some output. Suppose we are giving the input as xt and getting the output as yt, and this system has already, you have studied, may have studied in the control system, this system had unit impulse response of ht. Okay, so we can write yt is basically the convoluted output of xt into ht. Okay, similarly, if we this is the time domain, this is the time domain. In case of frequency domain, frequency domain. So in case of frequency domain, suppose this is a system, so I am doing the Laplace transform. So this is basically the Laplace transform of time domain system to the frequency domain system. So Laplace transform. So if we do the Laplace transform of time domain systems to frequency domain system, so this input becomes xs and this is ys. Then we can say the output is nothing but the multiplication of xs into hs. So we basically analyze our most of the circuits in the frequency domain so that the analysis become easier, because in the input we have to convolute the input and also the with the unit impulse response of the system. But here what happens, here we simply multiply the xs with hs and we get the output, that is ys. So this is basically a Laplace transform of each of the things and we can easily get the answer. So here also, so the transfer function refers to transfer function tf, we can often written as ts. This is nothing but ys divided by xs of the circuit. So here ys divided by xs is nothing but hs, so this is known as the transfer function of the circuit. Okay, yeah. So transfer function generally we discuss in the frequency domain, and we can say that this is a Laplace transform of output divided by Laplace transform of input, provided that all initial conditions are set to 0. Okay, so this is the definition of a transfer function. So now here we are discussing about the hj omega. So what is hj omega? This is s is nothing but basically sigma plus j omega, right? So sigma, this is the real part and this is the imaginary part. So sigma refers to attenuation of any system. Attenuation means loss of any system. So if we consider a lossless system, for lossless system where attenuation is 0, for lossless system s is basically replaced by j omega. So if we replaced by j omega over here, so we can say transfer function which is t of j omega, which is nothing but y of j omega divided by x of j omega, which is h of j omega. Okay. Okay. So in this question also, here it is asking what is the transfer function of the circuit shown in the figure. Okay, so we should find out what is the VOS versus VIS. Okay, so we know that in the Laplace domain, and this is the uh, time domain. Okay, so the time domain, if there is a register R, then in Laplace domain also we can consider it as R. If there is a C capacitor, then we will consider 1 by SC in the Laplace domain, and if there is a L, we can consider it as SL. Similarly, all the other thing also, if VIT, this is the input, then we can say VIS, this is the in Laplace domain, and VOT, we can say VOS, this is the Laplace domain. Okay, VOS. So these are the things. Okay, fine. Yeah. So now, mm, here also we are seeing that this is a you should always look at the circuit and can analyze that what is the configuration. Here also it is the ideal op amp, and here also it's a negative feedback is there because there is a feedback path between the output to the inverting terminal. So basically this is a virtual ground concept holds here, virtual, not virtual ground, virtual short concept holds here. So whatever will be the V plus, that will be the V minus, and also we are giving some input, so there is some input is there, so vi. So here it is basically mm, we can easily use the KCL and KVL, we can easily use the KCL and we can solve this problem, right? So how we can solve this problem? So here the V plus, the voltage V plus will be, V plus is nothing but, so it is a voltage, using the voltage division formula we can say V plus means V plus in the S domain. Okay, we are analyzing it at S domain. So S domain is nothing but VIS into, this is R1 divided by R1 plus 1 by SC. Okay, this refers to it's SC. It will be Vi of S, it will be of VO of S, right? Similarly, it is V minus S domain and it is also V plus S domain. Okay, so this is the V plus S. So according to the virtual short concept, V minus S should be equal to V plus S. So this is VIS into R1 into SC divided by 1 plus SCR1, that is SCR1 into VIS divided by 1 plus SCR1. Okay, yeah. So now we know the V minus S, and here also it's a VIS. So if we apply any the current flowing through this, so VIS minus, this is V minus S divided by the resistance R2 is equal to V minus S minus of VOS divided by the output resistance, this feedback resistance R2, because no current flow in this op amp, right? It is ideal. Okay, so R2 cancels out, so we can write about VOS is equal to twice of V minus S minus of VIS. Okay, so this is V minus S. Okay, okay, so we can write it as 2 into VIS into SCR1 divided by 1 plus SCR1 minus VIS. If we take the VIS common, then it is 1 plus SCR1, here 2 SCR1 minus 1 minus SCR1, right? So it will be VIS into SCR1 minus 1 divided by 1 plus SCR1, or even in a simplified manner we can say minus, if we take the minus common, then it is 1 minus, always it is better to write the equation 1 plus 1 minus S like this in this format. Okay, so I am using the so I am taking the minus common and I am writing in the form like 1 plus S something or 1 minus S something like that. Okay, so the transfer function HS should be VOS divided by VIS, which is minus 1 minus SCR1 divided by 1 plus SCR1. So now in the given option, okay, so it is asking about the in the j omega form. Okay, so h of j omega will be nothing but minus 1 minus j omega CR1 divided by 1 plus j omega CR1. Okay, and now it is asking about the okay, so if we consider this minus 1, minus means minus 1 as k, so it will be k into 1 minus j omega CR1 divided by 1 plus j omega CR1. So this will be the transfer function. So here okay, so here basically here it is considering the omega 0. So I will discuss about the omega 0 later also. So omega 0 basically refers to 1 divided by R1C. Okay, so here if we consider this thing, so k 1 minus j omega by omega 0 divided by 1 plus j omega by omega 0. So this omega 0 is nothing but 3 dB cutoff frequency, 3 dB cutoff frequency, 3 dB cutoff frequency. Okay, so if we consider this as a 3 dB cutoff frequency, then it will come as 1 divided by R1C. Okay, and if we replace in that, so we'll get k 1 minus j omega by omega 0, 1 plus j omega by omega 0. So the correct answer will be option B. Okay, okay, okay. So how we are getting this 3 dB cutoff frequency, we will look in the next problem. Okay, yeah. So I am going to the next problem. For the op-amp filter in the figure, the filter type and the 3 dB frequencies are okay. So here we will discuss about the 3 dB frequency, how we are getting and what is the meaning of this. Okay, So what is the thing? This is the op-amp filter. So this is basically the op-amp, and there is some resistor and the capacitor combinations are there. So it is acting as an op-amp filter. So how the filter, what is the filter type, whether it is a high pass filter, low pass filter, we should know, and we should determine, and also what is the 3 dB frequency, cutoff frequency, that we need to determine. Okay. Okay. See, this is an ideal op amp, so this is ground. So this terminal is according to the virtual short concept. This should also be ground. That is, it is also zero. Okay. So now, so we can analyze this problem by two method. Okay, one is based on intuition, and second one is by detailed analysis. So I am doing the detailed analysis at first, and then I will discuss about the what we can do by using the intuition. So basically, based on the question, you can easily analysis using the intuition, that you will see in the next method. Okay, so I am discussing about the method 1 by detailed analysis. Okay, yeah. So now here it is v minus. Okay, so similarly vis minus v minus s divided by r1 is equal to v minus s minus of v0 s divided by r2 parallel 1 by sc, right? Because this remains r2, but this c will become 1 by sc. Okay, yeah. So v minus s is basically 0 because it's ground, so virtual ground concept is 0. So vis by r1 is nothing but minus v0s divided by r2 parallel 1 by sc. So if we do r2 into 1 by sc divided by r2 plus 1 by sc, so it will be minus v0s, this is r2 divided by 1 plus sc r2. Okay, so if we do v0s divided by, we need to determine this thing. This is basically the transfer function, ts transfer function. So this is minus r2 divided by r1 1 plus sc r2. Okay, yeah. So this is the basic thing, this is the basic transfer function. So now if we uh, write it in Fourier domain. Fourier domain means Laplace domain, while sigma is equal to 0, that is known as Fourier domain. So t of j omega is nothing but minus r2 by r1 1 plus j omega c r2. Okay, so now so this is the transfer function that we got. Okay, so we have done this KCL analysis, but simply you can write using this. You have already known that this is a negative feedback, and it's also ideal op amp, and this is the input is applied in the inverting terminal, so it is an inverting amplifier. So according to the inverting amplifier, the output divided by input is basically minus RF by R1, right? So what is in the feedback part and what is the input resistance? So in the feedback part there is 1 divided by SC parallel R2 divided by r1, right? So equal to minus r2 1 by sc divided by r2 plus 1 by sc divided by r1. So it will be minus r2 divided by r1 into 1 plus sc r2. So same thing, right? Yeah, the same thing. Okay. Okay, so now so this is the transfer function, t of j omega is like this. And now how can we how can you determine that whether it is a low pass filter or high pass filter? For low pass filter, so basically we put at first we put omega is equal to 0. So omega is equal to 0 means frequency is 0, right? F equal to 0, that means DC. if the input is in DC, then T of j omega, that is T of 0, will be nothing but minus R2 divided by R1, right? Minus R2 divided by R1. If we put j is equal to 0, okay. In the second case, if you put omega equal to infinity, that means frequency equal to infinity. That means infinite frequency AC signal. Infinite frequency means frequency very high AC signal. Then what we get? T of 0 is equal to, so omega is equal to infinity. That means this T0 becomes 0. So that means for the low frequency we get an output, but in the high frequency we get 0 output. So this is basically a behavior of low pass filter. So this is low pass filter. Okay. So how you can draw this low pass filter? So if this is the thing, so that means it will behave like this. So for certain low value of frequency it will conduct, and after that high frequency it will not conduct. Okay. So suppose this is the A, this is the magnitude. So if you so this is mod of T of j omega. So this is, if this is A, and this is the omega axis, right? So it starts from 0. Okay. So this is the thing, and this is the basically a behavior of a low pass filter. This behave as a LPF, low pass filter. Okay. Now we have to determine what is the 3 dB frequency. So what do you mean by 3 dB frequency? The 3 dB frequency means, so here the in the low pass filter, from the graph we can see. So basically so this has two value. One is the magnitude. What is the magnitude value? This is minus R2 divided by R1 root over 1 plus omega square c square R2 square. Okay. So we are plotting this thing over here only. This thing is T of mod of T of j omega, right? Okay. So basically what is the thing? So now what happens is, so the omega 3 dB cutoff frequency refers to that frequency when the output becomes 1 by root 2 times what is the output at omega equal to 0. So if at omega equal to 0 point it is A, then at whatever frequency it will become A divided by root 2, that is known as omega 3 dB. Why it is omega 3 dB? See one thing. So A by root 2, so this transfer function, that is mod T of j omega, that becomes mod of T0, that is at 0 dB frequency, divided by root 2, or you can say 20 log 10 of mod T of j omega is equal to 20 log 10 of mod T0 minus 20 log 10 of root 2, right? Minus means because it's in divide, so it will be minus. So if we do root 2 and then log of that and multiply it with 20, we can get minus 3 over here. So this is minus 3. Okay. So minus 3. So this is the minus 3 dB, because we are converting it in dB, right? This is in dB, this is in dB. So this is a minus 3 dB. So if we plot this thing, that means 20 log 10 mod T of j omega, then at this point this difference becomes 3 dB less than whatever is the output at omega equal to 0. Okay. Yeah. Okay. Okay. So here what will be the uh, what will be the output? So at T0 the output is minus R2 divided by R1 So this is the output. So now at 3 dB mod of t j omega at 3 dB will be minus r2 by r1 divided by root over 2. So if we compare this equation with this, then we can get that root over 1 plus omega square c square r2 square is root over 2. That means omega square c square r2 square is 2 minus 1, which is 1, and similarly omega square is 1 divided by c square r2 square, or omega is basically 1 divided by r2c. So this is the frequency after which, this is the frequency omega 3 dB cutoff frequency after at which the magnitude falls root 2 times of this. Okay, yeah, okay. So this is the thing. Okay, okay. So here the value of omega 3 dB will be, so this is a low pass filter, and the omega 3 dB, omega 3 dB is 1 divided by r2c. That means 1 divided by 8.2. So what is the frequency they are asking? So they are asking about the f3 dB. F3 dB is nothing but r2c. This means f3 dB is equal to 1 divided by r2c into 2 pi. So into c 50 nanofarad into 2 pi. Okay, so 8.2 into 10 cube into 50 into 10 to the power minus 9 into 2 into pi, and 1 divided by answer. So this will come as 388 hertz. So the correct answer will be low pass filter 388 hertz. So option B. So option B will be the correct answer. So it will act as a low pass filter and it has a 3 dB frequency of 388 hertz. Okay, okay. So this is the concept about the omega 3 dB or 3 dB cutoff frequency. Okay. So one more thing, this 3 dB cutoff frequency. So 3 dB cutoff frequency means where the voltage, if there is some amount of voltage or current or something like that, it will fall by root 2 times. Okay, but it is also known as half power point. Why half power point? Half power point. Half power point means because suppose there is some p0 power at omega equal to 0, so it will fall p0 by 2. Why? Because if we do 10 log 10, so 10 log 10 p0 is equal to 10 log 10. This is the power, p becomes p0 divided by 2. So this is p0 minus 10 log 10 2. See, if we do log 2 and multiply it with 10, that also refers to 3 dB. So this refers to 3 dB. So this 3 dB cutoff frequency, that refers to half power point. That is, at this point the power becomes 1 to half of the power at omega equal to 0. Okay, yeah. So these are all the things. So in the previous problem also, in the 3 dB cutoff frequency, similarly we have decided that it should be 1 divided by r1c. Okay, yeah. So moving forward to the next problem, what is the form of a transfer function for the circuit shown in figure? So it is shown in figure. Okay, so sorry. These are the generally this is a detailed analysis, but if we want to do a intuitive analysis, then how can we do the intuitive analysis? I am just showing that. Okay, so that was the method 1. And now if we discuss about the method 2, this is method 2. So in the method 2, how we can analyze this thing? So this is the circuit. So here it is ground. Okay, so this is the ground. So this is the C, this is the R2, and this is R1, and this is VI, and this is VO, and this output, there is a output resistance which is RL. Okay, so how we can do using the intuitive analysis? So this is 1K, this is 8.2K, and this is 50 nanofarad. Okay, so suppose by looking at the question, what we can do at omega equal to 0, at omega equal to 0, what happens? That means it in DC condition, right? DC condition. Omega equal to 0 means S is also equal to 0, right? Because S is equal to J omega. S is equal to J omega. Okay. So at omega equal to 0, what happens? This C in Laplace domain, it can be written by 1 by SC. So if we put S is equal to 0, that means it will be 1 by 0, that means infinity. So it will offer an infinite resistance, that means this 1 by SC is nothing but the impedance, equivalent impedance, right? Z of C, right? Yeah, so it will see a infinite impedance, so that means this circuit will be act as an open circuit. So S is equal to 0, so that means ZC is 1 by SC is equal to 1 by 0, that means infinity. So it will be act as an open circuit, and if it acts as an open circuit, then V0 divided by Vi will be nothing but minus R2 by R1, right? Because it acts as an inverting amplifier. Okay, similarly, if omega is equal to infinity, that means infinite frequency AC signal, infinite frequency or more frequency, that means more frequency AC signal. If we go to high frequency AC signal, what happens? That means S tends to infinity, so the equivalent impedance of the capacitance ZC will be 1 divided by infinity, that means 0. So that means this capacitor acts as a short circuit. So if it is acts as a short circuit, so V0 will be equal to 0 because it is ground. So this terminal will also be ground, and that is short with the VO. That means it should also be ground. So that means these two terminals are ground. So V0 is equal to 0, that means V0 divided by Vi is equal to 0. Whatever be the input, irrespective of the input, output will be equal to 0. So that means at omega equal to 0 we have some gain, but at omega equal to infinity we have no gain. So that means it will act as a low pass filter. Okay, yeah. So this is the intuitive analysis how we can do. So you can apply this method in any of the question, and you can easily say that whether it will be a low pass filter or a high pass filter. Fine. For the next problem, okay, so in the next problem also we will do some intuitive analysis that we have just now gathered, which is at omega at S equal to 0, that means omega equal to 0, that means in DC condition the ZC, that is 1 divided by SC, this capacitor, this will become infinite, that means open circuit. So no whatever will be the input, that will not so irrespective of the input, so this will be 0. So that means there should this should be open circuit. So as it is open circuit, so that means no current flow in this side, so the no current flow in this side also, so VO will also will be equal to 0. And similarly at S equal to infinity, sorry, at S equal to infinity, that means omega is equal to infinity, that is AC means high frequency AC signal. The ZC is equal to 1 divided by SC, that means 1 divided by infinity. If we put infinity over here, then it will be 0, then it will be act as a short circuit. SC, that means short circuit. So if it is acts as a short circuit, so now that VO divided by VI will be minus R2 by R1, because the op amp will act as an inverting amplifier. Okay, so here we can see that at low frequency the output is equal to 0, but high frequency it has certain gain, so that means it will act as an high pass filter. Okay. Yeah. So you can easily say that it can act as a high pass filter. So by this analysis we can say this active filter, why? Because op amp is using in this filter. So this is the example of active filter. So this active filter is a high pass filter. Okay, now we'll do the analysis with a normal method and we'll see that what is the transfer function. Okay, so so we know this is a inverting amplifier, so that means the output VOS divided by input, that is VOS divided by VIS is equal to minus R2 divided by, this is in series, right? R1 and C is in series, so R1 plus 1 by SC, because in Laplace domain we are writing everything in the Laplace domain, so it is minus SC R2 divided by 1 plus SC R1. So this is the thing, right? Okay, so now what is so this T of S, or we can say this is H of S, H of S equal to minus SCR2 divided by 1 plus SC R1. So if we put J omega, so minus J omega CR1 divided by, sorry, CR2 divided by 1 plus J omega CR1. So now whatever is the what will be the cutoff frequency? So the cutoff frequency will be written as 1 divided by R1C, right? So you can write it as minus J omega CR2 divided by 1 plus J omega by omega naught. So this minus 1 and CR2, this forms the K, so it will be K into J omega divided by 1 plus J omega by omega naught. So this will be H of J omega. Okay, so this is the thing. So the correct answer will be option D. Okay, yeah. Okay, so remember one thing, for the high pass filter, for the low pass filter, the transfer function will be in the form of K divided by 1 plus here in the in this problem. Yeah, okay, so in this problem this is K into S divided by, means it should be 1 plus S into some value, that is CR1. Here it is CR1, so it will be in this format only. And so in this thing you can derive like omega 3 dB 1 plus SC CR1, but using this formula we can see that 1 plus S divided by omega 3 dB, and from here you can determine the omega 3 dB as 1 divided by R1C. Okay, this is the 3 dB cutoff frequency. Okay, so what is the form of the transfer function of the circuit shown in figure? Okay, so okay, so now how we can do? So here it is a voltage, so you can easily see this is an ideal op amp, and it also has some negative feedback. Okay, negative feedback. So virtual short concept holds. So you need to determine what is the V plus. So V plus of S is equal to Vi of S into, this is a simple voltage division rule, R plus 1 by SC, that means VIS SCR divided by 1 plus SCR. Okay, this is the V plus S. Now here if we apply, So 0 minus V minus S. So according to the virtual short concept, V minus S should also be equal to V plus S. That means it is equal to VIS into SCR divided by 1 plus SCR, right? Okay. So now here the current flow through this 0 minus VIS divided by R1 is equal to VIS minus of VOS divided by R2, right? Okay, R2. So now what you are getting, so this thing, it is VOS equal to VOS divided by R2 is equal to VIS divided by R2 plus VIS divided by R1. Okay, if you take VIS common, you can get R2 R1 plus R2. Now this R2 and R2 cancels out, so you will get VOS is equal to, this R1 will be 1 plus R2 plus R1, R2 by R1 into VIS. Okay, so now if we put the VIS 1 divided by R2 plus R1, VIS is nothing but uh, sorry it will be V minus S. In everywhere it will be V minus S, V minus S, V minus S, V minus S. Okay, this is V minus S because this potential is V minus S, right? Yeah, so this V minus S, if you put from here, it will be VIS into SCR divided by 1 plus SCR. So HS, which is VOS divided by VIS, is equal to 1 plus R2 by R1 into SCR by 1 plus SCR. So if you do H of G omega is equal to 1 plus R2 by R1 into G omega CR 1 plus G omega CR. Okay, so now you know that this 1 by RC, 1 divided by RC is omega naught, so you can say 1 divided by R2 by R1 into C into R in other side, G omega divided by 1 plus G omega by omega naught. So you can write K, this term as K into J omega divided by 1 plus J omega by omega. So according to the answer, the correct answer will be option A, K into J omega divided by 1 plus J omega by omega. So this is the transfer function. Okay. Okay. Yeah. So so far what we have discussed, so far we have covered this basic op-amp transfer characteristic. What will be the transfer characteristics curve of this op-amp, and then we have determined what is the transfer function and of this filter and how it behaves, like is it a low pass filter or it is a high pass filter. And also we have discussed about the 3 dB cutoff frequency of any filter, active filter, that is either high pass filter or low pass filter. Here also we have determined the transfer function of the particular circuit. And now, yeah, so now we will move to the next part, which is the precision rectifier. So this is known as a precision rectifier. So precision rectifier problem. Okay, yeah, okay, fine. So the op-amp circuit is shown in figure along with the input voltage, which graph correctly describes the output waveform. Okay, okay, so I am drawing the circuit. So this is minus, this is plus. So this is Vi, and here it is connected to the output Vo. It will be R, and here it will have some diode D. Okay, yeah. Now what is happening? Let's say, see. Okay, so now uh, the input or the op-amp circuit shown in the figure is along with the input voltage transfer. Input voltage is varying from 1 volt to minus 1 volt peak to peak. Which graph correctly describes the output waveform? Output waveform, what will be the output waveform? Okay, okay. So to analyze this problem, what we can see, when Vi is equal to 0, then what is happening? When Vi is equal to 0, that means this terminal is also equal to 0, and this result as Vo is equal to 0. So this is the case 1. Okay, okay. For case 2, what is happening? If Vi is small positive, if it is small positive, then what happens? So Vi is small positive, that means the difference to this op amp is V plus minus of V minus, right? So this is a small positive, small positive. If it is small positive, so it will be a small positive signal that is going to there, small positive. So what is happening? So here also, if it is going positive, so here it has a large negative voltage. That means, so Vd, this is increasing, so that means small positive. So the output, that is Vo, is AOL time VID. If it is not connected in the feedback path, AOL VID, that is this small positive voltage is enlarged in the output, so it will be a large positive. So large positive voltage means the diode becomes on. So diode becomes on, that means diode is short circuit. Short circuit, diode becomes on means diode becomes short circuit. Then what is the case? Then the equivalent circuit diagram will be, this is minus, this is plus, this is Vi, and here the diode is short, like this. Okay, it is short. So now this is Vo and this is R. So basically whatever is the input, that will appear here, because it's a virtual short concept, and according to that the output will be like this. So it is basically a buffer circuit, right? Buffer circuit, so it will act as a buffer circuit. So buffer circuit means the output will follow the input Vi. So whatever you are giving in the input Vi, that will appear over here, and this Vi is short with Vo. So Vo is basically equal to Vi. So for small positive Vi, what is happening? I am repeating it again, that the different signal that is applying to the op amp is small positive, because it is V plus minus V minus, and the small positive voltage becomes amplified, and it becomes a large positive, and it appears at just at the right at the output of this, that is Vx. This is Vx is large positive, Vx is large positive, and if Vx is large positive number, then it is enough to turn the diode on, and if the diode is on, then it will behave as a short circuit, and as a short circuit, the diode so it will be there will be a short circuit path, so the equivalent circuit becomes like this. And if the equivalent circuit becomes like this, that means whatever input we are following, this is a basically a voltage follower circuit. That means whatever the input we are following, so that will be also applied in the negative terminal, that is the inverting terminal, and that is shorted with the output. That means the output will follow whatever is the input. So this is the case of a Vi small positive. Okay, yeah. And what will be the uh, case 3? In the case 3, if Vi is small negative, if Vi is small negative voltage, then what happen? Then Vd, it is V plus minus of V minus, right? So it is a small negative voltage. So now it will get amplified at the output, that is Vo is basically AOL into VD, you know all. So it will be largely amplified and it will have a large negative voltage across the diode. And now now the diode actually turns off because there is a large voltage in here Vx, and large negative voltage, and it is a basically V0 is basically 0. So it will be it is a negative bias. So basically that means this is currently off and it will act as an open circuit. So the equivalence diagram for the case 3 will be, so it will be minus, it will be plus, it will be Vi. So the diode becomes off. Okay. So this is the V and this is the R. So basically here this is not connected. So as a result, this VO becomes 0 volt. So VO will result in a 0 volt and it will have a 0 volt. So whatever if the output input is, if we plot the output also against it T and it is V0, so whatever we get whenever the Vi is small positive, that is if it is a positive, then throughout this cycle, so if we draw like this, then whatever the positive side it will get passed and in the negative side it will be 0 like this. So it will act as a half wave rectifier. You remember, right? We have already discussed in the earlier classes also that how the half-wave rectifier formed, and what do you mean by half-wave rectifier? Half-wave rectifier means only half of the waveform is passed. Okay, so here it is passing only the positive half. So this thing is passing and this thing is passing like that. Okay, yeah. So the correct answer among these will be option A. Half of this input is passing and then it is not passing and it is passing. So whenever this Vi is positive, then the voltage VO output is followed. VO is following the input, and whenever this Vi is negative, that will turn the diode off, and as a result, the VO becomes 0. So this is a basic property of a half-wave rectifier, and this is known as a precision rectifier. That is using the op amp and the diode to get the particularly operated rectifier. So this is known as precision rectifier problem. Okay. Okay. So I am moving forward to the next problem. In the next problem, it is said an op-amp circuit shown in the figure along with the input voltage waveform, which graph correctly describe the correct output waveform. Oh, so it is the same waveform we are giving, but now the circuit is now different. So, okay, at first I need to draw the circuit. Yeah. So what is happening? Okay, yeah. So now this is the op-amp circuit shown in the figure. Input voltage waveform, which graph corresponds to the output waveform. So what is happening? See, case 1, what is happening in here? If Vi is greater than 0 volt, if Vi is greater than 0 volt, then what is happening? For small positive Vi, for small positive Vi, so if we increase this, then there will be some current flowing, and for this small positive Vi, so if we denote this as Vx, the op amp output Vx is large negative, right? Because it is connecting in the inverting terminal, right? Vi is whatever is the Vi, so it will be a large negative because it is getting amplified over that, right? You already know the inverting you have already seen that Vo divided by Vi is equal to minus R2 by R1 in case of a inverting amplifier, right? So it will be a large negative. It is a small positive number. It will multiply it with the gain and it will appear as a large negative, that is Vs is large negative. So Vx is large negative. As a result, hence so it will be negative means the D2 will be off and D1 will be on. So this D1 will be on, that means it is short circuited path, and D2 will be off. So the equivalent circuit becomes, this is the R1, this is negative, this is positive, so this is Vi, so it becomes short circuit, it is on, but here it is off. So that means, and here we have R2 and this is V0. That means this V0 is basically 0 volt, because no current is flowing through the this resistor, right? Because this is off, so it will be not connected to this, so no current will be flowing. So this is 0 volt, this is also 0 volt, this is also 0 volt, and no current will flow through this. So that means this is in the off condition. Okay, so this V0 is equal to 0 volt. And case number 2, if we analyze the case number 2, if we analyze case number 2, that is Vi is less than 0 volt, that is for small negative Vi, the op amp output Vx is large positive. So if it is large positive, what happens? If it is Vx is large positive, op amp output Vx is large positive, then that means if it is a positive, that means D2 will conduct and D1 will not conduct, right? Because it is a p terminal, connected to p terminal, it is connected to the n terminal of D1, right? So D2 conducts and D1 not conducts. Okay, so the equivalent circuit will be, so D1 is not conducting and D2 is conducting, that means R1, this is Vi, this is negative, this is positive, and this terminal is, this is non-conducting, but this is conducting. Okay, so this is V0 and there is a feedback path also, this is R2, right? R2. So then we can see, so now this Vo versus Vi, so this is nothing but a inverting configuration, so it will be minus R2 by R1. And what is the value of R2 and R1? It is given like 1 kilo ohm and 1 kilo ohm, right? So it will be minus 1k by 1k, that is minus 1. So the output will be minus Vi. Okay, yeah, so this is the thing. So it is a case of a small negative voltage. Okay, yeah. And if we put Vi, case number 3, if we put Vi is equal to 0 volt, then what happens? If Vi is equal to 0 volt, we can easily see this is 0 volt already, so this is also 0 volt, no current is flowing through this, that means no current will flow through this, and Vo will also equal to 0. So Vo is equal to 0 volt. So the graph should pass at from the origin, that is 0 0. So how can we draw the graph? So it is Vi, So the output will be like, so if it is T, it is VO, what happens? So whenever Vi is positive, then VO is equal to 0 volt. So whenever this Vi is positive, this is positive, so that means this is 0 volt, and whenever it is negative, the VO is equal to minus of Vi, that means it will be get inverse like that. But whenever Vi is negative, VO will be minus of that, that means VO will be positive. So this will be the graph. So the correct answer will be option C. Okay, yeah. So this is also a problem of a precision rectifier. Yeah. So the next problem, the op-amp circuit is shown in the figure along with the input voltage waveform. Which graph correctly represents the output waveform? Okay, yeah. So here from the circuit you can easily see that this is basically a buffer circuit, that is a voltage follower. So this is nothing but a buffer or voltage follower circuit. Voltage follower. Okay. So now we need to analyze this circuit. So how it is going to be? So similar analysis. So Vi small positive. Now Vi is applying in the negative terminal, right? So output, if let us consider it as Vx, then Vx is nothing but large negative. So Vs is large negative, that means this diode will be off. If diode is off, then what will be the circuit? So minus plus, and here also we have certain R, and it is open, right? Yeah. So diode is off means open circuit. Open circuit. Okay. Yeah. So now this is going to positive terminal, and in negative terminal it is connected to output of this VO. This is Vi, this is R, this is R. So basically here the Vi voltage will appear across this, so it is Vi, and as it is connected to a so the as virtual short concept, this should also be Vi, and this is a voltage follower circuit, so the VO output will be also equal to Vi. So this is the case. And in the second one, say in the second case, how it is happening? In the second case, Vi is equal to small negative. When Vi is equal to small negative, what happens? Vx is becomes a large positive number, large positive. So if Vx is large positive, that means the diode is on. So when the diode is on, then what is happening? This output Vx, so the equivalent circuit will be, so it will act as a short circuit, and this is a short, right? Okay. Sorry, this is plus and this is minus. Okay. Okay. This is VO, this is R, this is R, this is Vi. Okay. So now what is happening? So here we can see that it is a inverting op amp. So Vx, whatever the voltage over here, that will be Vx is equal to, this is the inverting op amp, so Vx equal to Vi into minus R, this R, divided by R, this is this R. Okay. So it will be minus of Vi. R cancels out, minus Vi. So Vx equal to minus Vi. So the output is nothing but a voltage follower circuit. From this, if Vx is applied, then Vo will also be equal to minus of Vi. VO is equal to Vx, which is equal to minus of Vi, right? Yeah. So if we draw a diagram, okay, so how it can be? Okay, so suppose it is a T, it is a VO. So whenever Vi is positive, then VO is also positive, and whenever Vi is small negative, then also this VO is minus Vi, that is, it is positive. So it is a basic property of a full wave rectifier. So it will act as a full wave rectifier. The correct answer will be option D. Okay. Yeah. Right. Okay. Okay. So the next question: what is the phase of Hs at a frequency 2 Hz as obtained by Bode approximation? Okay. Yeah. So now we have already discussed about the active filters, and also we have discussed about some of the precision rectifiers, and now we're going to discuss about the Bode approximation, the Bode-Plot. Okay. So Hs is 20s divided by s plus 100 into s plus 1000. Okay. So so if we plot, so it has two plot. One is the magnitude plot, and also it has some phase plot. Okay. So if we convert it in Fourier transform, h of j omega is nothing but 20 j omega plus 100 j omega plus 1000. Okay. So this is the thing. Now what is happening? Okay. So if we plot the magnitude plot, if we do the magnitude plot, then what is happening? So suppose we have some transfer function. From this transfer function we want to draw some magnitude plot, that is the Bode-Plot. In the Bode-Plot we are taking 20 log 10 mod value of Hs, and this is in omega. So this omega is in log scale. Okay, this is in log scale. Okay. So here it has 1 0. So here it has, this has numerator or denominator. So in the numerator, if you solve the numerator you get the zeros, and if you solve the denominator you get the poles. Okay. So here the zeros, it at 0.0, so it will be from here. So remember, it is omega is a log scale, it will never start from 0. Okay, because log of 0 is not defined, so it will not 0, it is not 0, not 0. Okay. Yeah. So it will be like this. And remember one thing, that for zeros, so what are the zeros and poles? So here in this function zeros are, so z1, that is at 0 position, and it contributes 20 dB per decade slope. Okay. And similarly the poles, there are two poles p1 it at 0.100 and p2 is at 1000. Okay. So each of the pole contributes minus 20 dB per decade slope. Okay. Yeah. So now it will start with 20 dB per decade. So it is 20 dB per decade, and after it reaches 100, that is it is reaches to 100, that is p1, that is 100, it will be 0 dB per decade, because it was earlier it was plus 20 dB per decade, but now using the pole zero uh, that is the pole zero concept, so using this pole it will be 20 dB per decade minus 20 dB, that is 0 dB per decade. So it will go to 0 dB per decade, and after that after 1000 point it will go minus 20 dB per decade, so it will be minus 20 dB per decade. Okay, it will meter sometime. Yeah. Okay, so this is the magnitude plot. This refers to the magnitude plot. This is the magnitude plot. Okay, so similarly for this is the magnitude plot. Okay, similarly for the phase plot, the zeros contribute plus 90 degree and the poles contribute minus 90 degree. Okay, so now what will be the okay, yeah. So for the zero it contributes plus 90 degree phase, and for each pole it contributes minus 90 degree phase, right? Now what will be the phase plot basically? So if we plot, so it is omega, this is also in the log scale, and this is 20 log 10 angle of hs. Okay, angle of hs if we consider, so at first, so it will be 90 degree, it is 0. So because of this it is 90 degree, because of what, because there is a 0, that means that will contribute plus 90 degree, and then due to pole at 100 it will be contribute minus 90, that is it will be turned to 0. Okay, 0. And then so now remember one thing, at the pole point it will be 45 degree compensation. Okay, so p1 equal to 100 if you take, so it will be 45 degree. Okay, okay. Similarly there is another pole, so here also it will be, it will have minus 90 degree, so it will be, sorry, yeah, so it will be minus 90 degree. So now this pole p2 will be, so this is for minus 45 degree, this is minus 45 degree, this is p2 equal to 1000. Okay, okay. Second pole, so each pole contribute minus 90 degree. So earlier for 0 it was 90 degree, then for pole 1 it is 0 degree, it turns into 0 degree, and for pole 2 it turns into minus 90 degree. But remember each thing, that pole at particular the pole point the phase shift occurs as 45 degree. Okay, so this refers to the phase plot. This refers to the phase plot. Okay, now in the given question what it is asked, what is the phase of hs at a frequency 2 Hz obtained as Bode approximation? So now frequency is 2 Hz, that means omega is 2 pi f, that is 2 pi into 2 Hz, that is 4 pi Hz. 4 pi means 4 into pi, 4 into, that is 12.56 Hz. So 12 point from the graph also we can see 12.56 Hz is much less than 100, so somewhat near here. So at 12.5 Hz the phase angle will be plus 90 degree, so the answer will be plus 90 degree. So this is the answer based on the graph that we have drawn using this transfer function. And by another method also we can do by using the transfer function analysis. So here we can see that hs is nothing but 20s divided by s plus 100 into s plus 1000. Okay, so now as the s is too low, as at the rate 2 hertz frequency, using Bode-Plot approximation, the hs will be, so this s is much less than 100 or 1000. S is much less than 100 and s is much less than 1000, because s itself is low. S equal to j omega, and omega is low because f is low. So that means the s is very low. So if we ignore the s in this equation, we get 20s divided by 100 into 1000. So that means this will be s divided by 5000, and h of j omega will be j omega divided by 5000. And if you take the angle, so it will be tan inverse, this is omega divided by 5000 divided by 0, that means tan inverse infinity, that means 90 degree. So it will add plus 90 degree. So the correct answer will be option C. Okay, the next question, what is the phase at a frequency 4 kilohertz? So now here frequency is 4 kilohertz, that is 4000 hertz. That means the omega value will be twice pi f, that is twice into pi into 4000, this much radian per second. So 4000 into pi into 2, that is 25132.74, that much radian per second. Okay, so this is much beyond this thing. So we can see from the graph also, from the plot also, that this thing falls approximately at this point. At this point the phase is minus 90 degree. Okay, from the graph also you can see it is minus 90 degree. But if we want to do the analysis using the transfer function, so hs equal to 20s divided by s plus 100 s plus 1000. Now at f equal to 4 kilohertz, omega is very high, omega is very high, that means s is very high, and s is very high compared to 100 or 1000. So we can ignore this thing, 100 and 1000 in this equation. So s into s cancels out, so it will be 20 divided by s, or h of j omega is nothing but 20 divided by j omega. That means it will be minus j 20 by omega. So angle of h of j omega will be minus tan inverse 20 by omega divided by 0. That means minus tan inverse infinity, that is minus 90 degree. Minus 90. So the correct option will be option A, that is minus 90 degree. Okay. Yeah. Okay, question 11. So what is the slope of the magnitude Bode plot at a frequency of 500 Hz as obtained by the Bode approximation? So, okay, so what do you mean by Bode approximation? See, okay, so I have not discussed about the Bode approximation. Okay, so basically, what we can say, wait. Okay, so ideally the Bode plot will be like this, but in a real scenario, real case scenario, there will be certain, so this is not any sharp thing, so it will be like this. and here also it will be like this. Okay, so there are certain gap between these two. This is the 3 dB cutoff frequency, that is known as a 3 dB cutoff frequency. But when we are using the Bode-Plot approximation, Bode-Plot approximation, that means we are considering this sharp transition in our case. Okay, yeah. So now uh, here what it is telling, like in the frequency of 500 hertz, what will be the according to the Bode approximation, what will be the slope of the magnitude. So according to the given question, in 500 hertz, that means what is the value of omega. So frequency is nothing but 500 hertz, that means omega is equal to twice pi f equal to twice pi into 500, this much radian per second, that means 1000 into pi rad per second. So this is pi means 3.14, right? So 3.14 means this is 3140 radian per second. So according to the graph, 3140 belongs to this region, right? Greater than 1000. So in this region, the slope is minus 20 dB per decade, right? Yeah. So the slope of this will be, where it is, yeah. So the slope of this will be minus 20 dB per decade. Okay. Yeah. So the next question, what is the slope of the magnitude Bode-Plot at the frequency of 100 hertz? So at frequency equal to 100 hertz, omega equal to twice pi f equal to twice pi into 100, that much radian per second. So 2 into 100 into pi, that means 628.31 radian per second. So according to this graph, 621 that belongs to in this region location, 628. So in 628 it is 0 dB per decade, right? So it will be, the correct answer will be 0 dB per decade. It is the slope of the Bode magnitude. Okay, yeah. So the next question, which of the following transfer function corresponds to the magnitude plot shown in the figure? Okay, so this is the magnitude plot. So basically we can see that here is plus 20 dB per decade is there one, because in one the plus 20 dB per decade means what, 20 dB increase in a decade means 10 times of the frequency. So in one it has 0 dB, but in 10, in one decade it gains 20 dB, so it is plus 20 dB per decade. And here we can see that it is 0 dB per decade, 0 dB per decade. So as there is plus 20 dB per decade earlier, so it has some 0, right? And that 0 will start from certain point. So we can write the transfer function as hs equal to k into s, that means that will start from s at certain point, and then it has some pole at certain point, that is pole at point 10, right? And then only it will pole 0 compensation happens, and plus 20 dB per decade and minus 20 dB, 0 contribute plus 20 dB per decade, and pole contributes minus 20 dB per decade. So both cancels out and get 0 dB per decade. So that means at point 10 there will be some pole, so that will be 1 plus s by 10, right? We can write like this, s by 10. Yeah. And after this 0 dB per decade there are nothing changes, so this will be the transfer function of the system. So it will be hs equal to k s divided by 1 plus s by 10. So here it will be in the format of this, right? K, if we put the value of, okay, so just 1 second. Yeah, sorry. So now so uh, so if we solve this, k is divided by s plus 10, and it will be multiplied by s equal to k into 10s divided by s plus 10. Okay, if we put k is equal to 1, that means it is like this thing. Okay, so okay, so hs is basically k time 10 into s divided by s plus 10. Now we can easily find out the value of k. How we can find out? So we can put any of this formula, right? So 20 log 10 hs is basically, so at first we need to convert it in j omega format. H of j omega is equal to k into 10 into j omega divided by j omega plus 10. Okay, so if we write mod of h of j omega is equal to k into 10 into omega divided by root over of omega square plus 100, right? Now we put the value of this at omega equal to 1, the value is 0 dB. Okay, so 20 log 10 mod of h of j omega is equal to k into 10 into omega value is 1, right? So it will be 1, it will be root over 1 plus 100. So it will be 10, and like that you can calculate the value of the k. And if we put that, so the answer will be 10s divided by s plus 10. Okay. Okay. Uh, okay. So the next question is, which of the following transfer function corresponds to the magnitude Bode-Plot shown in the figure where k is a positive constant? Okay. So now here also how we can see, the at first it was 0 dB per decade. At first it is 0 dB per decade, 0 dB per decade. Then it becomes plus 20 dB per decade, and at last it becomes again 0 dB per decade. Okay, so if you write the transfer function hs will be k times what? So it has a certain rise in here, so it will be 1 plus s divided by 10, because at 10 there is some 0, so that's why it becomes 20 dB, right? 20 dB, 25 minus 5, that is 20 dB gain per 10 square by 10, that means 10 per decade. Per decade it is gaining 20 dB, divided by, then it becomes 0 dB per decade, so it will become 1 plus s divided by this 10 square, right? Because in 10 square there is a pole, for that only it becomes, so it will be 10 square. So it will be k 1 plus s by 10 divided by 1 plus s by 100. Okay, so it will be k s plus 10 divided by s plus 100 into 100 goes up, 10 goes down, so it will be 10 into k into s plus 10 by s plus 100. So sorry. Okay, so if we consider this as k dash, because it's a constant k dash, so 10 times k dash we can consider it as k, and it is s plus 10 divided by s plus 100. So the correct answer will be option C, k s plus 10 s by 100. Okay. So in the transfer function of question 14, what is the value of k? Okay, so now we have to find out the value of k. So how we can find the value of k? Here what is the transfer function? Transfer function hs equal to k s plus 10 s plus 100, right? So transfer function hs equal to k s plus 10 divided by s plus 100. Okay, so this is the thing. Okay, now how we can find out? So we are finding out at omega equal to 0, right? Because at 0 it has a 5 dB gain. So h of 0, s of 0, or we can write h of j omega equal to k j omega plus 10 divided by j omega plus 100, right? So h of 0, that is omega is equal to 0, that is k into 10 divided by 100. So this will cancel out. So h of 0 will be k by 10, right? Okay, so if we do log in both sides, 20 log 10 of mod of h0 is equal to 20 log 10 k by 10. Okay, so it is 5 given in figure. 5 is equal to 5 is equal to 20 log 10 k by 10. So k by 10 is equal to 10 to the power 5 divided by 20. So what is 5 divided by 20? 5 divided by 20 is 0.25. So it is 10 to the power 0.25. So k is equal to 10 into 10 to the power 0.25. That means 10 to the power 1.25, right? So 1.25 and 10 to the power of that. This is 17.78. So 17.78, that is close to 17.8. So this is the value of the k from here we can get. Okay, yeah, so this is the thing. And the next problem, which of the following transfer function corresponds to the phase Bode-Plot shown in the figure? Okay, yeah, so we can see that we have already discussed that 0 contribute 90 degree plus 90 degree positive and pole contribute minus 90 degree. So it was earlier 0 degree, so there is no pole or no 0, but here the phase shift is total minus 90 degree, so there should be some pole, so should be some pole. And as I have discussed earlier also, that the pole point will be at the particular pole point, the phase shift will be 45 degree, right? So here it will be a pole, so this will not be a pole, this will not be a pole, but this will a pole. So p equal to 10 is a pole. So if we write the transfer function, it will be k times 1 plus s by 10, right? So if we write is k dash, so k dash s plus 10 into 10. So 10 times k dash is equal to k, we are considering it k constant, some constant, divided by s plus 10. So the correct answer will be option A, k times s plus 10. Okay, so this was the last question. So that's all for today. So today I have discussed all of the topics like the basic op-amp circuit, then op-amp as a filter which is known as active filter, then some precision rectifier problem, and at last some concept about the Bode-Plot, how to construct a magnitude plot graph from a given transfer function, the Bode magnitude plot and Bode phase plot from given the transfer function, and also vice versa, that is if there is some magnitude Bode-Plot given or phase Bode-Plot given, then how to convert it to a transfer function. Okay, yeah, so that's all for today. If you have any doubt you can reach me, and you can also post in the discussion forum also. So that's all for today. Yeah, fine. We will meet in the next Tuesday. Okay. Thank you.